Hello friends, so today we are going to solve questions from rotational motion and these questions are from the year 2021. Total question we are going to solve 5 and all these 5 questions are from the mains. And for 2021 here this is part 2. In part 1 we also solved for the year 2021 12 questions, and this is the final part for this mains questions from the year 2021. Advanced question we have already done in our previous parts. So the first question, it states that moment of inertia of 4 bodies having same mass and radius are reported as I1 moment of inertia of thin circular ring about its diameter, I2 moment of inertia of circular disc about an axis perpendicular to disc and going through its center, I3 moment of inertia of solid cylinder about its axis, and I4 moment of inertia of solid sphere about its diameter. So based on this we have to find out which of these options hold the correct result. So it is quite straightforward. We are going to use our, you can say, take these bodies one over one and find out the moment of inertia formulas basically. So we start with I1, and I1 is moment of inertia of ring and about diameter, about its diameter. And we know that this question can be solved by using, you can say, two approaches. One, if you know the formulas directly you can make a comparison, and if you do not know the formula, like in first case I1 is with respect to diameter, but in the normal case for a ring the, you can say, moment of inertia for the, as a standard formula we take it about an axis which passes through the center and is perpendicular to the plane. That is a normal formula for our I1. So if you know the formula directly with respect to diameter you can just solve it there, but I'll take more traditional approach, consider the standard formula and from there derive what will be my I1. So we know that, okay, and in this case because it said that having the same mass and radius, so let us assume that our mass of all the bodies is capital M and radius for all the bodies is capital R. Okay. And we know that moment of inertia about an axis through the center, about the axis through and perpendicular to the center and please remember we are going to discuss first case with respect to a ring. Okay. And that moment of inertia, let us suppose we call this as I ring, and this I ring is our mr square. Okay. And Now we can use our perpendicular axis theorem, and so for this I ring we can just draw an approximate figure. So this is our ring, and the axis is passing through the center and is perpendicular to this plane. Okay, so this is the representation of our moment of inertia, which we are calling as I ring. Okay. And this ring is going to have two diameters. Okay, one we can take this direction, and other one we can take, you can say, let us call this as our Ix, okay. And second one will be our Iy, but this I ring is our as a Z axis. Okay. So Iy, now for the sake of representation, let me remove this part, and this will be my Iy. Okay, so all this, my Ix is perpendicular to my Iy is perpendicular to my Iz, but my Ix and Iy are in same plane. They are in same plane. So in this case, we can use theorem of perpendicular axis. We can say theorem of perpendicular axis, and which gives us that our Iz will be equal to our Ix plus Iy. And this, because the ring is our symmetric, so moment of inertia of Ix is with respect to also diameter, Iy is also with respect to a diameter, so therefore they will be equal. So we can say our Ix is equal to Iy, okay, and Iz is nothing but our I ring. This is our Iz. Therefore we can write that our mr square will be equal to, we can take any of the diameter. Let us suppose we take Ix. So this gives us that our Ix with respect to diameter is our mr square upon 2, and here Ix is nothing but our I1. So this is our I1. And we come to the next body, that is our I2 circular disc, axis perpendicular and going through the center. Okay. So we have a circular disc I2, moment of inertia for circular disc with axis perpendicular and perpendicular to the disc, and passing through center and through the center. So we can also draw, so this is our disc and axis is perpendicular passing through, and the moment of inertia is given as I2. Okay, so I2 will be nothing but moment of inertia for the disc. That is our standard formula. So we can write that our I2 will be equal to half mr square. we come to the third part, and third is our solid cylinder about its axis, which is given as I3. So I3 is moment of inertia for solid cylinder about its axis. And that is also our standard formula. So we can write that our I3 will be equal to 1 by 2 mr square. And then we come to our I4, and I4 is a solid sphere about its diameter. Moment of inertia for solid sphere about its diameter. And from here we get our I4 will be equal to 2 by 5 mr square. And let us check all the options. So at least we can say that our I1, I2 and I3 are equal. Okay. So we are having that, okay, so we can directly see that our option number 3 is correct, because all of them 3 are equal and they are greater than I4, because I4 is our 2 by 5. It has to be a smaller one, smallest one rather. So option 3 is correct. 3 is correct. Next question. It states that a uniform thin bar of mass 6 kg and length 2.5 meter is bent to make an equilateral hexagon. The moment of inertia about an axis passing through its center of mass and perpendicular to the plane of the hexagon is, this should be 10 to the power minus 1 kg meter square. So we have to find out the multiple. So we are given that mass of a bar is given as 6 and total length of this bar is given as 2.4, and hexagon is having our 6 sides. So we can find out the length of each side for hexagon. So we can say that each side of hexagon, let us suppose that it represented as S, will be equal to our total length of the bar divided by 6, which comes as 2.4 divided by 6, giving us 0.4 meters. Okay. And we can also find out the mass of each side, or we can say mass per side. Mass per side will be our total mass, that is our M, and let me call this as small m, will be equal to capital M divided by our 6, and we have 6 kg divided by 6 is giving us 1 kg. And So if we assume that our hexagon is lying in xy plane, then the axis will be perpendicular to plane, which is basically our z axis. So we can say that for hexagon in xy plane, we can say that axis of rotation is through center of mass and perpendicular to plane, or we can call this as our z axis. And so we can say that our so in this case, first of all, we can solve this question by using two methods. First is by considering a circumradius of a hexagon and find out its inner radius. And the second one, we can use a direct formula, and that formula is also called as a polygon formula, which is going to give us value of theta, and from there we can move forward. So first of all, let's calculate use the approach for our circumradius of the hexagon. Circumradius of hexagon. And for a regular hexagon, the circumradius if that is represented as capital R, or we can say the distance from the center to a vertex. Circumradius R is distance from the center to the vertex. Equals the side length. This is the basic property of our circumradius of a hexagon is equal to side which is side length, and side length we represent it as S. Therefore, we can say that our radius R will be equal to our side length S, which is equal to 0.4 meters. And now we are going to find out the inner radius, and you can say inner radius, suppose that is represented as small r, which is basically distance from the center, distance from the center to the midpoint of the side. To the midpoint of side, and for that we have a standard formula that our r is equal to square root of 3 divided by 2 multiplied by s, and this comes as square root of 3 divided by 2 multiplied by 0.4, and this gives us this. Our r is approximately equal to 0.3464 meters. Now let us calculate our moment of inertia. Moment of inertia, and first of all we are going to find out the moment of inertia of one side. Okay. And we just found out that one side is having a length of 4 meter and its, you can say, mass per side is 1 kg. Okay. Therefore we can say that our moment of inertia of one side about an axis through its center and perpendicular to its length. So basically here we are considering a straight rod whose length is s and axis is passing through its center. Okay. And this is ultimately will be our, and for the other one this will be something like this and all like this. Okay. So for all the sides of the hexagon we are going to find out with respect to the its center of the axis passing through the center and perpendicular to its length. So we can say that our I through its center of mass for a single rod, we know the formula is our 1/12 ms square, and we know all these values, so this comes to 1/12 multiplied by our and mass is about 1 kg and side is 0.4 square. So we get this is approximately equal to 0.0133, and we just found out that the rod's center is at the inner center, which is R. Okay. Therefore we are going to use parallel axis theorem to find out the moment of inertia about the hexagon center. So we can say that parallel axis theorem moment of inertia about hexagon center. And we know that the hexagon center is at a distance r, okay, which we call as in radius. Therefore we can say the moment of inertia of the side will be equal to moment of inertia of our center of mass of the rod and plus mr square. And if we substitute values, we get this as ICM we just calculated is our 0.0133 plus mass is our 1 and this radius r is our 0.3464 whole square. So this gives us moment of inertia for the side is approximately equal to, this will be coming as 0.133 and we are having 6 sides. So total moment of inertia that is our I will be equal to 6 multiplied by moment of inertia of the side, and this gives us 6 multiplied by 0.133 and this giving us that the value of I is 0.8 kg meter square, and we can write this as 8 into 10 to the power minus 1 kg meter square. So we get the multiple will be our 8, and we can use the polygon formula also, that is the second approach. So we can say our alternate approach and this alternate approach is based on polygon formula. And we know that a regular polygon of n side and mass distributed, total mass is m and circumradius is capital R. Same parameters, but now we are going to use the formula. So the basic formula is that we have a regular polygon which is having n sides, and we have total mass is capital M, and we consider a circumradius is capital R. Therefore, we can write that moment of inertia about and okay, 1 second. Here, let me make one correction in this part. Okay, we have to remember that if this is the rod, then the axis is perpendicular to the rod. Okay, so which basically means that this, if this is our x-axis, then our this moment of inertia will be along our y-axis. Okay, there was some mistake in my previous explanation. Okay, and let me draw this. This is our y-axis about which we are going to find out the moment of inertia, and if this is the center, then the axis about which we are using a parallel, you can say parallel axis theorem. So axis will be passing through this center C, and it will be once again parallel to y-axis. Okay, so perpendicular to this entire plane. Okay, there was some representation problem, so we can just draw it as a cross. Okay, and here also we can represent it as a cross. Okay, cross a dot, basically it is perpendicular to the plane. So both the axes which is passing through the C as well as y are parallel with each other. Y is perpendicular to x-axis, which we have used with respect to our this center of mass. Okay, there we have used. Okay, so next is moment of inertia about an axis through the center and perpendicular to the plane, and that formula is our I is equal to mr square divided by 3 1 plus twice cos of pi by n. Okay, so this is our standard formula for moment of inertia passing through the center and perpendicular to the plane. So in this case, suppose we are having a hexagon, and this particular formula is directly based on the axis which is passing through the center, like this. Okay, and we know that the number of side for hexagon is 6, so we can easily find out our angle, which will be coming as pi by 6. Okay, so let me directly solve it. Mass is our, you can say, 6 kg. Okay, please remember this is total mass. Okay, so you can say that this is our total mass for entire polygon, which is our 6 kg. So we get I is equal to 6 multiplied by our 0.4 whole square divided by 3 and 1 plus 2 cos of pi by 6, and this we are going to get same answer, that will be 8.74 into 10 to the power minus 1 kg meter square. So we can just approximate it to 8 into 10 to the power minus 1. So either way we can just solve it. Okay. Next question, we are given that a sphere of radius a and mass m rolls along a horizontal plane with a constant speed v0. It encounters an inclined plane of angle, this angle should be theta, and climb upward. Assuming that it rolls without slipping, how far up the sphere will travel? Okay. So in this case, it is rolling without slipping, so obviously there will be two types of energies associated with it, translational and our kinetic energy. Okay, and if we say that, let us suppose it reaches, this is the maximum height and this height is given as h, and the slant height, a slant distance rather, is suppose taken as our s. So we can use the conservation of energy. You can say that translational plus kinetic, rotational will be equal to the potential energy at the maximum height. Okay, so it is going to start from point A and ultimately reaches maximum point, that is B. So we can say that rolling without slipping therefore total kinetic energy, which is suppose K, will be equal to kinetic energy translational plus kinetic energy rotational, and this is with respect to point A. Okay, just beyond point A, fraction of upward. And there is a rolling without slipping, so therefore if it is having a angular frequency, angular velocity omega, therefore we can write that our omega is equal to V naught upon A. This is also the condition for rolling without slipping. So we can say the total kinetic energy K will be equal to, translational will be equal to over half m V naught square plus rotational will be over half I omega square. And I we know that a moment of inertia formula is standard, omega we know in terms of V naught, so we substitute them. We get this as our half m V naught square plus this is half moment of inertia is given as 2 by 5 ma square, and omega we get this as V naught upon A whole square. Here this 2 and this A square goes by this square, and we get that total kinetic energy K will be equal to our half m V naught square plus 1 by 5 m V naught square, and 10 we have LCM, and we are going to get this 7 m V naught square. And potential energy, that is at maximum height, so we can say that potential energy at, or we can say potential energy gained, that is our U will be equal to mgh, or we can write this as mg s sine of theta, and we can use conservation and equate them. So we can say conservation of energy total kinetic energy K should be equal to over U. Therefore we can write that our 7 upon 10 m V naught square is equal to our, one second, the answer, okay, we need to find out S, and this comes as mg s sine of theta, so which gives us that our S will be equal to, here this m and m cancels out, so we get this as 7 V naught square, and we have 10 g sine of theta. Okay. And in this case, actually when it came into the examination, all the options were wrong. Okay, none of the options basically matched the given answer. But in this particular case, we have, you can say, took the correct answers, and this gives us that the option number B is the correct option. Okay. In actual, when the NT asked this question, there was none of the options matching with the given options, given solution. So you can see option B is correct. B is correct. Next question. It states that 4 identical solid spheres, each of mass m, radius a, are placed with their centers at the 4 corners of square of side B. The moment of inertia of the system about one side of the square where the axis of rotation is parallel to the plane of the square is. So we can draw an approximate figure. So we are given a side, and the length of the side is given as B, and at each corner we are having identical solid sphere whose radius is, mass is m, and radius is given as a, and we have to find out that moment of about one side of square and axis is parallel to the plane of the square. Okay. So we can pick any one of the side, and then we are going to find out its, we can say, with respect to the other part. Okay, so in this case we have to remember that first of all we have to find out the, let us call this as the center of all this sphere. Let us call this as P. Center of the sphere is Q, R and S. So first of all we are going to find out the moment of inertia of any one sphere with respect to their center. Okay, because all the sphere are same. So like we take this first one, so we are going to find out the moment of inertia of this sphere with respect to point P, and then we can use theorem of parallel axis to find out about the you can say the required format which is asked in the question. And here let us say that, okay, let's mark their coordinate. We take as origin, so we can say our S is our origin, so this is having a coordinate 0, 0. Then we come to our R is our B 0, 0. Then we come to our Q is our B, B, 0, and then we come to our P, and P will be our 0, B, 0. And let us assume that the axis of rotation is along side SR. Along the side SR, and we have taken that this is our x-axis and this is our y-axis. So along SR basically means that y is equal to 0 as well as z is also equal to 0. Okay. So we are going to use, first of all, let's find out the moment of inertia of a single sphere about its own diameter. Okay. So you can say moment of inertia of a single sphere along its own diameter. And let us call this as I, because I center of mass Cm will be equal to, that is standard formula, 2 by 5 m r square. Here r is our a square. And with respect to axis of rotation, we can write that therefore by parallel axis theorem we can say that for each sphere the moment of inertia about axis of rotation which gives us moment of inertia, if that is represented as I, so I will be equal to, with respect to their, you can say ICM plus mass, and suppose the distance is given as d, that is d square, and this d is the perpendicular distance from the sphere center to the axis. That is our basic parallel axis theorem. So we are interested in finding out this d. Okay. So let's find out this d, distance from the axis. Distance from the axis. So like I said, that the axis which we are taken is along SR. Okay, so it means both the spheres which are lying at S as well as R, this distance d will be equal to 0 because they are already itself on the axis. Therefore we can say spheres S, which is 0, 0, 0, and our R, which is our B 0, 0, the axis passes through the center. The axis of rotation passes through their center. Therefore we can say d is equal to 0. Thus you can write that moment of inertia of sphere A will be equal to moment of inertia for sphere B, and putting d is equal to 0 in this equation, we know that our I is equal to our ICM. So this will be equal to our ICM, which is our 2 by 5 MA square. Now we are left with two other spheres. And we can say that spheres, we are having P and Q. Q is our B comma B comma 0, and P is our 0 comma B comma 0. The perpendicular distance is D. Okay. So we can clearly see that we have taken the axis of rotation. This is our axis of rotation, and the perpendicular distance, this is also B, and here this is also our B. Therefore, we can say that our IC and ID will be equal to our ICM plus MB square, which gives us 2 by 5 MA square plus MB square. Now we can find out the total moment of inertia, that is summation of all the respective individual moment of inertia. So you can say total moment of inertia, which is our I, is equal to IA plus IB, IC, and our ID. And we can just reformulate it. We can write this as twice of IA plus, sorry, 1 second. This is our S and R, and this is our Q and P. Similarly here also, this will be S, R, P, Q. So this will be our twice of S and twice of our IP, which gives us 2 times 2 by 5 MA square plus 2 times 2 by 5 MA square plus 2 times MB square. I would say quite a simple calculation. We get this total moment of inertia will be equal to 8 by 5 MA square plus 2 MB square. So we have 8 by 5, 8 by 5 and 2 MB, that is option 3 is correct. Correct. Next question. It states that a cord is wound around the circumference of a wheel of radius small r. The axis of the wheel is horizontal and the moment of inertia about it is I. A weight is attached to the cord at the end. The weight falls from rest. After falling through a distance h, the square of the angular velocity of the wheel will be. So in this case, we are given that we are having a wheel, so it is some kind of a ring, and suppose this is the center of the ring, and to this and its radius is given to us as small r, and the axis is horizontal, and okay, and to this a cord is wound, and to the other end of the cord we are having a weight. Okay, and yeah, and this weight, suppose this initial position and it falls downward, and this is a final position, and the distance by which it falls is given as capital H, is given as h. So as it is going to fall, this wheel is going to rotate, okay, and it is going to rotate about an axis which is passing through its center, and the moment of inertia of that is given as I. Okay. So here we can use our conservation energy, and then we are going to solve it. Okay, so we can say that so in this case we are going to do it in a considering that this is our initial position, and this is our final position. And we are going to assume that the final position is at the ground level, okay, such that at this final position the potential energy is equal to 0, okay, and at initial position its potential energy will be equal to mgh. Okay, we are going to do it like this way. So we can say that initial position, initial potential energy of the weight and initially it was at rest, and at a height, that height is of h. So therefore its initial potential energy, that is our u of I, will be equal to mgh. Now we come to the final energy, and as it is going to fall, there will be the rotation of the wheel. Okay. So the final potential energy in the final position will be equal to 0, but there will be the translational kinetic energy associated with the weight, as well as a rotational kinetic energy that will be also associated with the weight. Rotational kinetic energy will be associated with the wheel, okay, and translational will be, we can write that in the format of this weight also. Okay. So we can say that final energy after falling distance h So we can write that potential energy final, which will be where U of F is equal to 0, and we are going to have the translational kinetic energy of the weight of weight, which will be equal to our K translational is equal to half mv square, and then we are going to have rotational kinetic energy of wheel, and this can be K rotational, which will be equal to over half I omega square, and these are rolling without slipping, therefore we can say our V is equal to omega R. So we can say the total kinetic energy, final kinetic energy total, that I suppose that is given as K, which will be equal to our K translational plus K rotational, and we get our K is equal to half mv square plus half I omega square, and the moment of inertia is I, so we are going to keep it like that only, and we can substitute our V is equal to half m omega R whole square plus half I omega square. So this gives us that our K will be equal to half omega square mr square plus I. Now we can use easily our conservation energy. So we can say energy conservation we can say that our potential energy initial is equal to kinetic energy, one second, let me call this as Kf, is equal to final kinetic energy, and we get mgh is equal to over half omega square mr square plus I, and now it is quite straightforward. We get our omega square is equal to 2 mgh, and we can write this as our mr square plus I. So the option will be 2 mgh plus I, and yes, option 2 is correct. Option 2 is correct. So in this particular question, this is the important thing, that our two types of kinetic energy will be associated, okay, because the wheel is going to rotate. So we have written specifically that the rotational kinetic energy is with respect to wheel, and translational kinetic energy we have written with respect to the weight. So this completes all the 5 questions and completes the part 2 for the year 2021. So all the main questions for the 2021 has been completed in 2 parts. Thank you.